Hello, everyone, and welcome to the September 17th Air Devils meeting. I am your host, Daniel, and our co-host slash resident RC aircraft expert, Evan Draganchuk, is going to be presenting an intro to RC aircraft. Going to be showing off some of his collection. And yeah.
All right. Are we ready?
Yeah. I will
I forgot
pin your
something.
video.
What?
You're pinned. You are now the
Okay.
main focus.
I need to get my iPod. I put my notes on that, so I'll be back in like 30 seconds.
Okay. So yeah, like I was just saying to those of you who have just joined us, next week will be an intro to CAD, computer-aided design. For that, I recommend that everyone download SolidWorks. It is free for you to use as an ASU student. You can just go to the My ASU, My Apps, and then SolidWorks. Follow the posted instructions, and you will be able to have your own very nice license of SolidWorks that you can then use to design a sensor payload that we will then drop from a building and have it fall to the ground. I think that will be neat. All right. Evan?
Are you ready?
Yeah, take it away.
All right, so let's see here. There you go. That's a little better. I'm in my garage. So just kind of what this is. I am renting a house with my roommates. So I am originally from Florida, but out here, and we're in apartments, and couldn't really do too much airplane stuff there. And now that we're renting a house, got a garage all to myself, there's airplanes all over. So it's kind of addictive. They take up all your airspace, and now I got a lot of things to show you. So
yeah,
we got a couple of things here. We got the competition plane and prototype from last year for the club, so that'll be interesting to see what actual techniques we're using, and then also techniques that are used in like the actual like RC model official manufacturing world. So let's see, I have my phone charging because I forgot to do that, but I think we're ready to go off here. Let me flip my camera around. How do I do that? Oh, there you go. All right, so kind of just do a little overview of everything right now. Got a couple gas planes with nitro engines and other things. And then here's our competition plane from last year. So we're gonna kind of more go over the like construction aspects of all this instead of, we're gonna kind of save the electronics and such for another presentation. But I need to open this up. 1 second. And then I got more stuff in here. It's crazy. But so this is our competition plane from last year, and this is what we came up to for our carrying a payload inside a fuselage. We have a hatch here, and I came up with a nice little solution of some plastic tabs that are screwed into the side kind of stringer rib here. Or it's not a rib, but it's a stringer there. So that's what we have, a nice little, oh, you gotta look where I'm pointing. There we go. Nice little attachment point there. A little extra, oh man, I don't remember where my camera is. A little extra wood there to support it all. So that's going to be kind of what we're talking about overall, is how you actually build these things. Because as you see, once we actually figure it out, we got, or when it's fully done, I mean, is a couple hundred pieces really. So I guess here we'll start on the fuselage. So what we do is we like to use a keel. So that's more what this carbon fiber is. And got some dogs out here. So we got a keel here, and then we're able to calculate the forces a lot easier than having to have an actual fuselage and calculate the forces off of all the side pieces. So everything else you see here is just to shape the fuselage, and the only real structural component is this carbon fiber, which is pretty interesting. So if you cut the carbon fiber, the fuselage will pretty much break in flight, which might happen because we have a slight little, let's see if we move it over here. The team hasn't really seen this, but right around here, you can't see it, but on this little corner, there's a crack about 6 inches long or so on both sides, I believe.
Oh, geez, both sides, 6 inches.
I think it feels. Oh, maybe it might just be this side.
Okay.
I think it's not this side. But if you squish it, you could definitely feel and hear that there's a little crunchiness.
Yeah.
But it's not really that
deformation.
bad. So it looks fixable. But so that's our main structural component, and that goes up. If we open this back up, that goes up through a little bend through the back here when we have all our little servo wires follow it, and that connects to the tail pieces. So as we see, we got our tail pieces here, and then, oh yeah, I covered it up real nice, but we drilled a couple little holes in this carbon fiber rod here for our tail and rudder, or vertical and horizontal stabilizers, to have their own ribs, or what is it called? Spars going through them. So we could kind of see, I covered it up here, but here's a spar that's going to be going the whole length, and it goes through our tail piece of the fuselage and then out to the other side. So that's one piece, and it connects in the middle, which makes it very strong. And then all we have is some balsa ribs to give it shape. And then we have a little secondary spar to stop the torque aspect. And on this one, we have little, you can't see it here. We have little plastic hinges that we put in, and we got to glue them in on each side. And that gives us our hinge point. And then we have a control horn, a surface control horn. So we got an elevator. So this would be called an elevator control horn, connecting to your servo. And then this piece is called your servo horn. So those are the pieces that actually give you the movement. And then you have a push rod or a control rod as that piece. And then there's a couple of different ways to attach them all together. So this is like a part that you really don't want to fail. And actually, this isn't the best method of doing it, but it's the easiest. This is called like a little quick connector, and it has a little set screw on the top there, and that will friction fit it to the control rod to give you any perfect distance you want this rod to be. So you could set your control surface to, you want it to be nice in line. So without having a method to set your thing, then you have to have the servo kind of do it, and then you mess up your control throws and such. So a little quick connect, set your distance, and then you tighten it down, and you hope it doesn't slip. So that's the one thing, is the only thing holding this from stopping it from slipping is just the friction force, which is over time, and if you have vibrations from the motors, this can loosen up. And it's probably a thing you should really check every now and again, but we don't really do that. It hasn't failed yet. And that kind of is the same thing for all the control surfaces on this plane. So if we move to the wing, we can see we have a nice transparent covering here. And just to show the bottom, we got a cool little pattern. Well, I got the transparent covering here so we could actually see what's happening. And we have our torque box here, which is part of our aero design. We have to calculate all the loads that the wing will have, and then we got to make something that will fit inside of your wing to support it. That's the big thing, is if you have your spar be too thick, then you're just messing up your airflow. So that's the cool thing about what our last year, our president, Nick, made a program that will actually calculate all this. And it fits in the wing. And it's an actual little box. So you have a top, bottom, and two sides, and then all the ribs will go over it. And some of the ribs will be stronger than others to support the loads on the box to keep it from deforming. And then in the center here, if we undo this, this is our attachment method for the wing to the fuselage, which is a pretty crucial thing because you got a lot of weird shapes of the wing trying to fit on the fuselage, and then you also want it to be strong and not move or twist, on top of also not being too heavy. So as we find in all aero things, there's compromises and a lot of parameters that we have to meet. And this is a nice big 3D printed part from our president this year. Daniel made this on his printer.
Actually, Christian made that piece.
Oh, that's right.
I designed it.
All right, there we go. We got teamwork.
Yeah.
So we got our piece here.
Show them the part that I missed on the putting on the fillets.
Fillets.
Yeah, like a lot of the parts are rounded on that thing, which is important because it helps keep it strong. But I actually missed one of the corners of the top piece.
Oh, I'm trying to think of what it.
It's
where
the
was it?
bottom left.
Oh, right here. Yeah. So luckily, I mean, that doesn't really do too much. But you see, we got nice rounded corners. And then this one, we could get a little stress crack right there if it had proper loads, which this is really overbuilt. So don't need to worry about it. But, you know, always a thing to consider. Might as well build it, you know, correctly, even if you don't have to. I'm doing a really bad job at aiming the camera. So if I'm not pointing at what I'm talking about, just tell me. But so here we have our mount, and it sits on top of our torque box. And I forgot when I glued it that we had big holes in this, so I just have a lot of extra glue. But the mount is also attached with a couple bolts to just ensure that it really won't go anywheres. So when possible, you want to have like different methods of attachment for pieces. So glue is I guess it's like a physical attachment or chemical or something. And then the bolts are more like mechanical. So it really can't fail. Like if the glue fails somehow, then you got the bolts. And if the bolts fail, then you got the glue. So that's just to ensure this piece doesn't fail. Because if it does, then your wing and fuselage separate.
Yeah, this piece really is the core of the aircraft. And if this thing fails.
Yeah, this took a good bit of designing. And on here, these aren't 3D printed parts. They're actually nylon bolts that come up from the bottom and are glued in before we actually glued this in. And then those bolts just give us actual attachment with real fasteners. So we got a little wing nut here, which just makes it easy to screw on and off if I can actually get it. So that's how the wing actually goes on. You'll notice some extra bolts here. Those actually go to the landing gear. So flip this over a little bit.
Yeah, this piece is like the main load-bearing structure of the aircraft. The main attachment, I guess, between the landing gear, which takes the loads on takeoff and landing, the actual spar, the box spar that takes the loads during flight, and the keel, which takes loads during maneuvering.
Yeah, so this is kind of like where it really all comes together.
Where exactly were we placing the cargo blocks and passengers in the fuselage, which were like towards the middle?
So on this one, we never really got around to finishing it. But if you see here, we have a little flat sections. So we would have a little floor that goes in here and actually sits above all the electronics. And actually have it over here that is kind of partly finished, but we never got around to doing it. But there you go. There's your passengers. They have a beautiful little foam sitting compartment. Keep them nice and comfy. And so, yeah, it's a little creative way of keeping it removable so you can work on it. And that's another thing that is really key to RC stuff, because a lot of things are really tiny and they could break, and then you got to replace it. So trying to keep all your components accessible is a big thing. But yeah, so that was our little payload compartment, and then we would have had another one in the front and the back for extra stuff if we finished it. But
Yeah, there was a passenger and then a cargo block requirement. Here's some of the
yeah,
passengers.
we got some of the passengers here and whatnot.
Those are nice, cute-looking passengers.
Yeah, we even got this was our first prototype for our wing, a 4-piece connection for our wing seat.
Yep, we had
So
to get
that
those.
that was going to sit and have the wing sit on that, and then we would have had to have another method to actually secure it, because this would line it up, but we didn't have a way to actually keep it on. We were going to use like rubber bands or something, but we just went with, or we figured out that this idea of actually having a cap to hold it solves all the problems.
Yep.
So we go through, multiple processes of stuff to actually get it.
Yeah, those pieces we got printed by ASU, and they messed up the order and they made them completely solid out of plastic, which means they're really heavy for not that much gain in structural.
Yeah, I think we drilled
bearingness.
we drilled those holes out manually for it.
Yeah, I spent a few hours trying to drill all those holes, but then we decided that, hey, you can just 3D print a better attachment block.
Yeah, what did you mean when you said it was printed by ASU? Like, who printed it?
There is a 3D print lab that you can send in your prints as long as you are a member of, as long as it's relevant for a student organization, they will print it for free. And so, yeah, we had the 3D print lab do it. And that same lab is also where we go ahead and get all of our stuff laser cut. And there's a lot of laser cut components on this plane. Like every one of the bulkheads in the fuselage is laser cut.
Yep, all these are laser cut. All the ribs to make the shapes for the aero surfaces are laser cut.
All of the ribs inside of the thing is laser cut. All of the wing box is also all laser cut and then glued together. Lots of
laser
lasers.
cut pretty much turn, parts into an actual kit, which is really cool. So here's our little landing gear attachment here. And the one problem here was, so we could get big landing forces if you mess up landing the plane. And since we have our landing gear attached to the torque box of the wing, we don't want to hurt the torque box at all, because that is structural to, your wing loads. So you don't want to have any crushes there. And we actually, before we glued this wing box together, we got a balsa block to fit inside of it perfectly. And this center section from about here, that much of this torque box is actually solid wood. Even though that sounds heavy, it's balsa wood. So it is quite light. And then the rest of this torque box is hollow. So the solid torque box in the center was just so when you had landing loads squish all the pieces together, you don't have any cracks. There's nowheres really for the wood to go if it's solid. So that's that. And then if we look on here also, we can kind of look at our motor mounts. And they're kind of sketchy now that I look at them some more. But on these motor mounts, we have a 3D printed part So 3D printed part going to your motor mount, going to your motor. So these motors, as you can see here, they are the brushless motors, and these are called outrunners. And that just means that this whole outer portion of the motor actually spins with the propeller. But that then has to, be held to the wing securely, because each of these motors will make about 5, 6, 7 pounds of thrust, and you don't want that going anywheres, which has happened in the past, and we learned from it. But so our motor mounts are glued onto a little foam block here to secure it. And then, as I was saying before, you always want more than one method of securement when possible. So here we have a zip tie going around a rib, and the zip tie goes all the way around it and then loops around back up. So somehow, if your glue does debond, then your motor would still be relatively in place instead of just fully actually falling off of the plane. It will kind of maybe dangle or be okay. And that could save you from crashing, which is always a good thing.
We have some videos of when the motor mount detached from the wing and violently attacked the wing, and it's not pretty.
Yeah, these motors are really powerful. You really don't you want to take them seriously when this thing's powered up, because it's quite scary. So if I move some of this over for a second, I'll get this plane out, which is a new purchase of mine. Move that there for a second.
One quick thing, can you show them the leading edge of the wing?
Yeah.
And also, I guess,
Oh,
the
maybe if I
top
do
of the
this.
fuselage?
There we go. I'll be better moving the camera now. Yeah, okay. So we can't really see too much of the leading edge of the wing because I covered it nicely in black. But, here we go. I can see a little bit here. So the leading, no, that's the problem. So the leading edge of our wing, we sheet in thin balsa wood. So you can see here, this is the center, and it's really not supported. But it's a 16th inch thick balsa wood, and we soak it in some water, some hot water, which makes it really pliable. And then you can see there's some lines in the balsa wood here, and those are the grain lines. So that's the way the tree actually grows. The tree grows that way, and lengthwise, I guess you could say. And that is the way that the wood likes to bend. It is strong in that way with the grain, and it is very weak this way against the grain. So you could fold stuff around pretty tight curves when you're going against the grain, and then when you have it supported with the leading edge of the wing, it makes a very strong and shaped piece. So the leading edge you want to have nice and strong, because that's where all the airflow first hits. And actually I have a plane inside. You can see if the leading edge isn't really sheeted too much, then you'll lose some of the curvature shape that you've made your ribs, and that's not too good when you've spent the whole semester designing a wing. You really want it to keep its shape throughout the build. But even with this way, if we look at it more this way, in between the ribs, it has a little bit of a dip because there's no supporting structure. So no matter what you do, unless you have a fully sheeted wing, which RC people do, you'll have a airfoil shape that isn't quite what you've designed. And that's just an aspect of building a wing light, and you gotta just realize that your wing will not be quite the perfect shape that you thought it would be. Yeah, there you go, like Daniel has.
This is a wingtip from a previous year that we had to make fully sheeted because we had no way of fitting other structure inside. And so, yeah, it's all balsa wood, hollow inside. I don't know if you can hear that.
Yeah.
And
Where's the main board which gets the signals from the remote that we have? And what was the material of the propellers? Could you please say that again?
So the propellers are made of these are just plastic.
Oh,
They are composite plastic. They have some type of, it's like nylon, I
Yeah, I
think
think they're
is
nylon reinforced.
yeah, nylon reinforced. Some of them have like some glass fibers in it and whatnot, but we buy them. We don't make any of this. This is just off the shelf RC, and they're very strong plastic. You break them in a crash, but that's about it.
Yeah.
okay.
And then
The
our
rules-
little controller. Oh, you want to say something, Daniel?
Yeah, the rules state that we can't use custom-made propellers. They have to be commercially available.
Yeah.
Oh.
Oh, this might be better. Another thing is, if you actually want to make a propeller, that these propellers at full power, they spin like 10,000 RPM, and you have to have them very balanced and each blade to actually be the same, or else it will give you a lot of vibrations or just actually rip apart, which
We had
would be
6S
bad.
batteries, right?
Yeah.
Yeah, they spin at like 24,000 RPM.
Yeah. That's, well, all right, so if we want to really get specific there, where we at 1,100 kV. So that the kV is a rating of without a load on it, Daniel.
Mm-hmm.
So that's like how fast it would spin without a propeller. But then with the propeller, from what I've read online, they usually spin 70%
Yeah,
of that
70,
number.
75, if you're lucky.
Yeah, so yeah, I don't know if you've added that in there, but 75% of like 25,000 or something is what we'd be spinning.
Yeah, with the 75% correction factor, it's like 18,000. So still really fast.
Yeah, 18,000 RPM, which is crazy because most cars go up to like 6,000 or 7,000.
Mm-hmm.
So anyways, as you were asking before, our little controller part, it's called the receiver. So this is our receiver here, and I have it just taped to the carbon fiber so I didn't have to glue it. So it's easily removable and quite secure. But we got the receiver here, and we got a couple antennas. So these receive your signal from your radio, and they go to the receiver, and then that transmits all your movements, your desires into these wires that go to your control surfaces. So that's how it works. And then we have a whole lot of thick wires here. These are the main power wires for the motors. And then one part of the rules is we had to have an arming plug behind the propellers. So the easiest portion of that I found was just all the way back here. So right here is our arming plug on the side of the fuselage that will arm your motors when you're ready. But
Yeah, it basically just completes the circuit, allows.
yeah, really simple, just switch, plug. But so as Daniel was saying before, this is another sheeted balsa part, and this turned out really well. I didn't think it was going to turn out this well, but so this is our top part. We were originally going to try to get this to be vacuum formed at the ASU Polytechnic campus. They have a vacuum former, and then if you have a mold, you could vacuum form a plastic on the mold and then cut it out, and then you have a very light shell. So the closest thing that I could have made by hand was this balsa and foam hatch here. So this was all hand built here. Oh, geez. I don't know what happened there. It goes black. Anyways, this was all hand built here. So I pretty much just took the shape that we needed and then cut multiple of those out. And then all this is just actually hot glued together. And then you hot glue it, and then you fold it over and just let the hot glue dry. And after you take your time, it will turn out really well. And this thing right here probably took, I don't know, like 2 hours to finish. But you get quality if you put in the time. And
If you want, like, if you get a chance of like going back and like changing some things on this aircraft, what would you want to do?
For this one,
Yeah, I was just wondering.
I mean, really, this one turned out really well. I think what we could have improved on is what I want to improve on this year is if we could just work on maybe making our parts a little bit more specific. So if you see here, we have a couple parts that just don't quite line up. Like we have a little extra hanging off there and whatnot. So I was thinking, since we have this is an idea, Daniel. If we have the CAD file for what the shape we want to make, we can print out on paper a building what is it called, instruction sheet, right?
Yeah, paper build templates.
Yeah, a little template. So because all this we do by hand by just measuring with a measuring tape, and that's it. So if we had like an instruction sheet, a building template where we know where the ribs go and what line they're in and what we need, and if we could just do that off the CAD file, we can make our parts really accurate, because that's kind of what we're missing here is some accuracy, which would just make the whole plane a little bit nicer.
Yeah.
I was trying to do some of that last year.
Yeah, like a 3D printed jig, I think is what Max is working on, but that kind of
Yeah,
fell.
it didn't print well at all.
Yeah.
And we abandoned it quickly.
Other things we could have improved. The nose cone could have been a little bit more aerodynamic, I think.
Yeah, it kind of cuts off quick, but
yeah.
That was like a 14-hour print just for this?
My parents got really mad at me when I was printing that at our house because the 3D printer is loud and annoying.
Yeah.
The fuselage attachment to the wing could have been lighter. Could have been
Yeah,
better
that was
designed. The tail surfaces could have been lighter, of course. I don't.
Yeah.
Like, our tail is really heavy compared to what it should be. The
one thing I will say, when I put this together, our weight and balance crew did a perfect job, and the batteries pretty much sat right where we predicted.
Yeah.
So
but
that's another thing. Yeah.
Could have saved a little bit of weight.
Oh yeah, for sure. But
yeah.
I mean, that's really about it. The whole plane turned out pretty well. We didn't have a very solid plan for our passenger compartment either.
No.
But the airframe was quite solid. I flew this multiple times, and it still can fly with just a couple minutes of fixing it. And we're probably going to do some tests with this plane, dropping those and towing those sensor designs in a little bit. So
yeah,
that'll be fun for the fly days when we eventually get to that.
Yep.
So if we want to continue, yeah. Was there another question? No, okay. If we want to continue, this is another plane. This is a production plane. So it was a kit that you would buy. It came as an almost ready to fly plane. So the airframe was complete, and you just had to add all your electronics into it. So this one has a little gas engine on it, which we don't use, and the competition won't allow. But if you look in the internals of this, is what's interesting, because this uses a fiberglass mold fuselage. So all this we see here is fiberglass, and my Sharpie marks are just pieces where I had to reinforce it, because I bought this from a guy who crashed it, and there was a couple spider cracks you see here from, you can see the fiberglass started to weaken. So I had to do some reinforcing on the inside. But this is another method to build a fuselage. So you use fiberglass and then a couple little ribs there just to keep the shape of the fiberglass throughout the build. I wish I had a flashlight. No, that doesn't help this way. I wish I had a flashlight, but you could kind of see in there what it's all about. And then another method of using your control surfaces is, so you see we have all our servos here in the center of the wing. And they have to use control rods to go down to your tail and rudder surfaces. Instead, on our fuselage here, we put our servos right close to it, so it makes it nice and simple. But the disadvantage of this way is you have more weight of all three servos all the way in your tail of your plane instead of in the center where the center of gravity is. And the weight of your servos don't affect your center of gravity. But since we have a weight and balance crew to work all that stuff out, we can compensate and plan for our servos being in the tail and not up front. So on this one, we have our, we'll do it on this side where it's brighter. This one, we have our servo and our control horn. And then that connects to this little piece. It's called the clevis. And that connects to a push rod cable. And you could pop this off and twist it with a little, is screwed on. So that will set your neutral point. So instead of using one of these quick connect pieces where you could just screw it down on the rod wherever you want, but this could slip, this part, there's no slippage. There's no way that this can move and come apart unless something actually breaks, where this set screw can get loose and this could slip. So on this plane, these two servos are our elevator servos, which are quite important. And then this one's just our rudder, which is not as needed for flight if that somehow loosens up. But that's another way to attach things and to control things. And on this one, we see down here is our receiver to control everything. We have some extra wires to connect to the wing. So that's pretty much it for like a fiberglass fuselage. We won't really, well, we can't really do this unless we had like full molds, and it's not worth it for one-off planes like we do.
Actually,
So
I just put this in the chat, but we might end up doing something like that for our main fuselage because the way our aircraft is going to look this year is going to look like last year's aircraft, but upside down. And so, with the keel on the top of the aircraft, and because our fuselage is going to be on the bottom, it's more likely to get damaged just in transport and moving. So we might try and do a fiberglass fuselage.
Well, we could also think about doing more of like a balsa sheeting too and stuff like that. A good thing, what a lot of people do with that fiberglass is you layer it in balsa, and then you put fiberglass, you put a layer of fiberglass and epoxy over top of it, and it turns into pretty much like a composite structure like carbon fiber where you have multiple layers. And the fiberglass in balsa makes stuff like really strong. So that could be a useful thing. But this one's actually full fiberglass, which you'll really only see in production model planes. So, oh yeah, here's another thing before we get done with this plane. So our wing attachment method on this one, we have two bolts on the back of the wing. So this is our wing seat. So the wing sits right here. So this is our wing seat. And then on the front, we have two little pegs. So on the wing, we'll have two little dowels that poke out like a 1/4 inch, and those will insert into here. And then you could drop the wing down, and these bolts will be removed. And then you bolt the rear of the wing to the fuselage. So then that gives you securement in the front and the rear. And then the wing sits on the two sides, so it stops it from wiggling around or anything. And if we look over here, this is the actual wing to the plane. So these are our little pegs. And then the little bolt holes are right there. And you can kind of see where the wing kind of sits. It kind of scuffs it up a little bit. But so that's how you attach this. This wing is this wing and this wing actually, they're both fully balsa covered wings. So you see They have a very smooth finish compared to this one, which you probably can't see too much on the camera, but it is slightly curved over each rib. The thing with these are the two outer surfaces, the top and bottom, they kind of take most of the flight loads. And for what we do is we want to predict the flight loads. And it's kind of hard to predict how well this surface that is all curved on both sides will hold up to strain. And so we just end up using a single torque box, which we could predict all the loads on. And so like on this fuselage here, how this keel is the only real structural piece on the whole fuselage, this torque box is the only structural piece on the whole wing. If you didn't have a leading edge or a trailing edge, well, I guess the ribs are structural. So you don't need any leading edge, trailing edge. You don't need anything else on this. And this wing will be as strong as it was without any of the covering. And this wing, it needs the balsa covering to really be strong. Sadly, you can see here there's some damage, and I crashed this plane in the spring, and I haven't fixed it yet. But the good thing is now we can see inside of it. So there's our balsa skeleton there. We got some little ribs and some little spars. And I got the rest of the wingtip here to show you a little bit better. So you see on here, we got ribs and spars inside the covering. So all these are like super light. They cut as many holes as they can into it to keep the inner structure light, because they don't need it to actually be strong, because the inner structure just keeps your outer structure rigid. So that's how these work. It would be an interesting idea to use, but since we as a DBF team, we have to calculate, flight loads for whatnot. We can't really do it with these wings. And so we won't be doing stuff like this too much. We will probably be doing some sheeting, like Daniel was saying on the fuselage could be a good possibility. That's about it for out here, I guess. This wing, I believe, yeah, so this wing uses that same method as the blue plane. It has 2 pegs and then 2 bolt holes. And then it has a little wing seat here. So you see, this is a little fiberglass part, and it curves to the shape of the wing to give it a nice fit.
Reduces form drag, aerodynamic fairing.
Yeah, so I could actually open this up too. Hopefully nothing will fall out too much. Okay. So this is the inner part of this plane. It's you can see this one is balsa sheeted also on the fuselage. So we see here the inner structure is just enough to keep the outer structure rigid and shaped. So we can have a couple stringers like we had in that first lecture, and a couple ribs or bulkheads. You could kind of call them each. And we can look, this way, there you go. Look back, just enough structure to keep it stable. But the problem is when you crash, a lot of pieces break. So this one needs some work, but it's not dead yet. So that's about it out here. Just give me 1 second. I have a couple other planes inside I could kind of show some examples of. So this plane here uses the same, we can't really see it, but the leading edge and half the wing is sheeted, and then the second half is our monocoque covered and ribs only. And this plane uses the same 2 pegs and 2 screws to hold it on. This wing is fully balsa sheeted. And this uses, again, it has 1 peg in the front and then 2 bolts in the back to hold it on. Oh yeah, here I could actually walk up to this one too. So this is another way to hold on a wing, which I have hanging up here. So this wing, it just uses rubber bands to be held on. So we have, well, actually my rubber band here broke, which is kind of bad, but we have two little dowels pegs that stick out of the fuselage on both sides. And then you just wrap rubber bands around the wing until you have enough to tightly secure the wing to the fuselage. The problem with this method, even though it is a very simple method, is if you do have so much loads that your wing lifts up, then it can depart the aircraft and your wing and aircraft separate. So you have to make sure you have enough rubber bands and they are in good condition.
Yep, they tend to
Yeah,
dry
yeah,
rot
that's
and
the
break.
Yeah. And then I guess on this one you can kind of see a little bit is some nose wheel steering action. So we got our nose wheel, and this is pretty much the same setup as we have on all the planes. You got a nose wheel, and this is a little spring is for some shock absorbing if you get a hard hit there. You have a little set screw here that locks onto a control rod. That then you have your push rod goes to your servo inside the fuselage. So, and then our landing gear mounts to the front plate here. So this is pretty much like the firewall. And then you have it securely mounted there. Actually, I forgot we have our prototype plane too. So if I just move this over. In the scraps on the side of the wall, we have long live the prototype plane. So this was what we were working on almost a full year ago now. And this is the very basic example of what turned out to be the competition plane.
It has
So
basically no structure.
Yeah, so as you see here, we cut out a foam wing. So this has a true airfoil shape throughout the whole thing. Each section here, you see we have 4 sections for half a wing, but each section has its own airfoil shape, which we've worked on, well, the aero team worked on to make the stall characteristics and the takeoff characteristics and whatnot, what we want. So this plane, we had to take off in 10 feet, so we had to have enough lift in the 10-foot distance, and then our motors had to have enough thrust to get to the airspeed to make the lift, and it all goes together. So this wing, our spar is a carbon fiber tube running the length, and then that's the only structural component really of this whole wing. The everything else is just kind of glued together to keep it there. Our ailerons on these really early prototypes are just taped on. So we cut them out, give them a little hinge point, tape them on, and that will be enough for a couple weeks of flying. And this one, we have a little rib here just for keeping our motor mount secure. And we don't have any secondary securement on this one, which this one worked. So I guess we did good gluing job.
Yeah.
But
on other prototype wings, we've had the motor fall off of the mount and wreak havoc.
yeah. Yeah, so on this wing, we could kind of see, this wing was from 2 years ago, but you could kind of see we labeled each section so we remembered. This has your little landing gear, a little landing gear mount there. And if we go to the fuselage, so the fuselage here was very
Fury
simple.
boards.
Yeah, this Fury foam board stuff is very strong. It's actually kind of heavy, but it is very strong. And we loaded this plane up in this little compartment here with, I believe it was 6 extra pounds on top of the battery weight and the plane weight. So this plane ended up being like 18 pounds with the payload, and we flew it, and it lived. So
yeah,
just
it has
looking,
basically no structure in it besides the foam board.
yeah, so that's just kind of a telltale sign of what you could really get away with. It's just our tail and rudder here is 1 sheet of foam, and we have a carbon fiber leading edge. They gave it some strength. So that really keeps this together. But as you can see here, we needed some bracing because this foam is so floppy that without having some extra mounting points, the thing was like really wiggly. But that's that. And the structure, yeah, pretty much none. Just pretty much the outer box, and that's about it. The best structured part is probably our landing gear here. Is we have a little flat plate to glue onto the foam, and then a little brace for our nose gear mount and servo. And that's how that goes together. So when you're not looking to keep a plane alive for long, you could get away with a lot. So that's our prototype plane.
You think we could have flown that at competition?
I mean, yeah, you could have. There was teams that didn't have much more than this, honestly.
Yep.
From last 2 years ago.
It has the school spirit aspect of having other people's projects
Yeah.
on the lid. Like, what's the title of the project that's on the top?
Using clinical, oh man, that's a big word. I don't know.
Neuropsychological?
Yeah. Assessments to predict motor learning in non-demented older adults. That's beautiful.
Yeah.
Yeah, so we got a foam plane. We got kind of a mix-up of foam and this covering, if we didn't know, is monocoat. It's a plastic covering. I'll have some over here to show you. So it's just these little rolls of pretty much plastic. This is a clear monocoat here, but it's pretty much just plastic, and one layer of it has glue on it, and when you heat it up, the glue becomes like liquid and it will stick to whatever is touching, and also the plastic will shrink when you heat it up. So that's how you are able to fit your monocoat on, and then you have a little iron and you rub it all around, and it will heat up, shrink, and get tight to your structure. And yeah, that's really about it. We got some of our carbon fiber building rods here, some of our foam board, some aluminum rods if we wanted to do a wing with aluminum. Right here is our very first test of trying to make a fuselage with a keel and some ribs, but we never finished that. I think we didn't have enough carbon fiber. Yeah.
Also really heavy.
Yeah, so that's about it for there. So you go inside, we have another plane or two to look at. We'll close the garage door there.
Just as a heads up, we're at about an hour, so.
Okay, yeah, I'm not going to be too much longer. Fish tank makes it all blue. Yeah, we could go to this one. So this is my current project. Luckily, my roommates are out of town right now, so I get to use the whole living room to work on a big plane. But so this plane here, if we look at it, it's another balsa built wing with monocoat covering. So you can see there's really not too much to it if you don't have the covering. But this one, instead of having our torque box as the spar, as the spar, it uses this wood and a couple different layers of wood. I can't get a good reflection. All right, there you go. A couple different layers of wood as the spar. So we have a square dowel on the top and the bottom, and then the front of it has a little bit more of a solid face structure. So that will take your compression and tension loads. And then since this single spar isn't quite enough, it also has a rear spar that continues the length to kind of double it up for the front and the back. And as you can see on this plane or wing, it doesn't have a sheeted leading edge. It only has just the very front is balsa, and then the rest isn't. So if you end up looking down, you can see in between the ribs it is slightly bowed, and that comes from when you make your monocoat tight, it shrinks, and then since there's no structure in the middle, it takes up whatever shape it wants. So that's not quite what you want. And there you go. You can see a good little reflection there of the shape not quite being the same throughout. It's close enough. It will fly fine. But this wing, as you can also see, each rib is exactly the same. It's pretty much one of the basic Clark Y airfoils. And with our plane, we make the wing very organic, I guess what T would say. It's very shaped. So we want to try to keep the shape as good as possible.
We have all sorts of magic, progressive camber madness in our wings.
Yeah, so not too much else to this one. If we look at the fuselage here, it looks really nice, but we might be able to do something like this as a fuselage if we wanted to, but we don't have a keel. So this, you can see, this is all laser cut balsa, or it might be light plywood, and they're all kind of, the ribs and the side pieces fit together, and you can see here where the pieces fit together. But once you have the whole box here, it makes the fuselage very, very strong, and it's not super heavy. This plane, for some reason, is actually quite heavy. I don't quite know where it all comes from, but here's a open structure skeleton of the tail and rudder pieces. So our plane for competition has an actual airfoil. So what's that? The NACA
0012.
Yeah,
0012.
0012. And this just has a flat plate airfoil with a very slightly rounded front edge and a very slightly rounded rear edge. And I mean, that's all you need for RC stuff, though. It makes it very simple, very easy to make. I think this was a kit. I bought it from someone again. I don't know. But as you can see, to keep it all strong, it has diagonal triangle bracing. And you could see the one thing what you want to do when you build is keep all your parts very tight. And you can see there's no gaps when you have all your angles come together. So this might have been a pre-made kit. I'm not quite sure. But all the pieces end up really close together. Makes it super strong when you glue it. And this one, again, uses a little locking tab in the front, which this one's really sketchy because it's so small. But it has just a little tab in the front. And then the rear has 2 bolts that hold the wing on. So that's it. That's what holds the whole wing on. This one, we have the push rods again. So we got the servos in the middle that kind of move the servo weight more forward. And the push rods go to the back. And then they pop out when they need to. And then you have one of those little clevises that are adjustable on a threaded rod. So to get your surface perfectly lined up, you twist this in and out a little bit and then connect it until it's perfect, and then you set it, and that's it. So that's about it for all the big stuff. The other plane we can see really quick. Oh, I have it hanging up here. So these are foam planes. These are just made out of foam board right here. Like we have, you just buy at like the dollar store, really, actually. And as you can see on these, is the foam makes the whole wing structure. So this is a symmetrical little wing airfoil shape, and it's just hot glued together. And all it is foam. It has a little foam spar running through the middle, and that's enough for small planes to stay together. The tail and rudder, just one sheet of foam, kind of like what we saw outside. And on this one too, you can see a little bit here. A little bit more. This one has a flat bottom for an airfoil, or a flat bottom, and then a little curved top for an airfoil. It's really rudimentary, but for small scale stuff, that's all you need. You can see the little spars right there. It's a little U shape in the wing, and you just hot glue it on. Hot glue your servos on. Hot glue your control pieces on, and that's about it. So that really kind of is an overview of all the possibilities in RC stuff. This is a little foam plane. This was a glider we made last year in our Air Devils. What was that? What was the glider workshop for the Vorlax?
Yeah, Vorlax stability.
So I Vorlaxed up this general plan form.
Isn't that
And
that's a demon, right?
yeah, I believe so. The F3D, I think, or
Yeah.
F4D. That's what it was.
Yeah.
But yeah, that's what it was supposed to be. Even though I think I kind of cut the corners kind of sharp. But as you can see here, it's literally one sheet of foam, and then it flies. So depending on how big you want to go, let's flip this around. So depending really on how big you want to go and how much you want to really put into it, you can make a whole lot of RC stuff. I focus a lot of that on our competition plane because that's what you're actually going to end up doing, and the prototype plane outside. So that's what we're going to really focus on. It's more of making sure our structures and loads are able to be calculated, and then we calculate them up, make sure they are good to go, and we build it. So that's about it.
Okay.
Is
All right.
there
Thank
really-
you, Evan.
Is there anything else you want to talk about there, Daniel?
Any questions from the group?
Yeah. This is it's an Edge 540.
All right. I'm gonna
Yeah.
stop the recording right there.